Thanks for the invitation, and it's great to be here. So today I'm going to talk about our recent work on understanding representation learning and use the theoretical understanding to derive new data selection algorithm to improve the representation learning. All right, so to get everyone on the same page, so let me give you an example of representation learning, how we use it in practice. So usually, this is called the multitask representation learning setting, where we have some source tasks, which is for training the representation. Usually, the source task can be, with a lot of data, and the goal is to train the representation. So the definition of representation is here. Basically, it's just a mapping from, say, input or image to the second of the last layer of your neural network. So, for example, you have mapped an image to this vector, and this is a representation of this image. Okay, and this representation function, it's this mapping from the image to this second to the last layer's vector. Okay, so what we do for representation learning, we use say ImageNet to train this neural network. Okay, say ResNet. And then we have a target task. That is a task we really want to solve. For example, here we consider this VOC7 dataset. It's a few-shot learning task. We have 20 classes, and each class only have 1 to 8 examples per class. So that's a few-shot learning task. Okay, so there's a big difference between using representation learning and without using representation learning. So if you don't use representation learning and you only use this small data set, okay, because you have few examples per class, you can only get 5% to 10% accuracy. Whatever method you want to use, like trees, neural networks, kernels, or linear functions, because it's a 20 class classification problem, even use random guess, you can get around 5% accuracy. So you cannot do much. But if you use representation learning using this framework, you first learn representation, and then you just retrain the last linear layer of this neural network for this target task. So you can boost performance from 5 to 10% to 50 to 80% accuracy. So that's a huge performance boost for this image classification task. So this is give you a flavor of why representation learning is so powerful in today's machine learning. All right, so this is only one example for image, but representation learning, this general idea, have been widely used in many applications, including natural language processing and graph representation learning, where we use, say, hidden state. Nowadays, we use transformer, and also we can use graph. We use graph neural network to learn representation for each node or each graph of the input graph. All right, so the first part, I want to talk about what are the theoretical foundations, the theoretical foundation of this multitask representation learning. So we'll talk about what are the necessary and sufficient conditions that permit the representation learning framework to improve the performance. So you can imagine if there's no, you do not put any assumption between the source task and target task, they are completely irrelevant, then you cannot hope to, this representation learning to improve the performance. So you need some conditions. I want to dig into what is the conditions that permit this efficient transfer learning from the source to target task using the representation learning framework. All right, to motivate the second part of the talk, there's a trend on big models. Okay, so when we use big models on big data, so this is a data size. Also, the data size here we use a 35 billion words to train the big language model, and for the model size, also increased as well. Nowadays, we use this large number of parameters in our model. Okay, so this is also belongs to the general framework of representation learning, and because those data used for training language models or other big model foundation models are very cheap. So you can just use as much data as possible in terms of the, because they are cheap, so you can just use it as possible if you have enough computation power. On the other hand, if you're not Google or Facebook or OpenAI, you are, say, a small company or you're at school, you don't have enough computation resource or money to really train those big models, you really need to develop some new methods to leverage this model, for example, if you have for your own data. Okay? For example, for GPT-3, there are 175 billion parameters in these 45 terabytes data. The estimated cost around $10 million to train the model. And I think most of the small organizations do not have this amount of money to train one model. Right? So a more practical scenario would be you have limited resources, which resource can be the money, the GPUs, or the engineers to pre-process those data. And on the other, also you have only one or few target downstream tasks, or basically target tasks you want to solve. So here it's different from the framework for GPT-3 or BERT, where you want to train one model and to use them for all kinds of downstream tasks. Here, suppose you only have one or a few target tasks that you really want to solve, and you want to leverage this foundation model or representation learning to improve the performance on the target task. So what you do with limited resource you have. So this talk, we will describe one method to give more efficient training for this kind of scenario, where you have a limited resource. So our main idea is to do data selection and task selection. So in multi-task representation learning, you have a lot of tasks to choose from to train your representation, but not all of them are really useful for your target task. So we want to really only select those relevant tasks for training the representation, so you can improve the training efficiency, also all the engineering burden of this representation learning step, instead of using all the data available if you are not, because you are not Google or Facebook. All right, so these are the motivations. Generally the resource needed scale with number of pre-training data need. So once you do some selection, you don't need to use all the pre-training data. Also, there's some recent studies showing that if you do some data and task selection, you can actually improve the performance, even if you can use all the data available. All right, so our general approach is active learning. So active learning is definitely not new. It's been well studied in machine learning for many years. But classical active learning mostly focus on single task learning, where you have a pool of data and you want to only select a few data to curate its labels. Okay, so that is for classical active learning. What we do is active learning for representation learning. Okay, so it's a different angle from the classical active learning. So we select, so our goal is to learn good representation, and our goal is to select which relevant tasks we include during your pre-training phase. Okay? And here, today I'll describe our work on task level active learning for the multitask representation learning setting. All right, so this is the outline of today's talk. I'll first talk about our work on supervised multitask representation learning about the theory. The key notion here to take away is the diversity of the tasks, which is important for multitask representation learning in this passive setting. And then I'll talk about our work on active multitask representation learning, where we need to define the task relevance between the source and target task, and use this relevance to sample data from the source tasks. Okay? And we will present some algorithms, theory, and experiments. All right, so let's start from the first part. All right, so to get a little bit more technical, let's describe the setting here. So this is a multitask representation learning setting where we have, say, big T number of tasks, and let's say inputs, there are x1 to x big T. So what representation learning do? We'll learn a common representation, which is this H function, okay, from the input to a representation layer, okay? And this, importantly, it is shared across all the tasks. So all x1 to xt, all these T tasks share the same representation learning layer. And then for the task-specific prediction, because I have T tasks, they have different labels, so you have a different prediction layer, which are this G1 to GT. Okay? And the composition of G and this H is your end-to-end prediction function from the input to the label. Okay. So this is a source task. We use the source task to learn the representation. And then for the target task, we'll fix this representation, which is a small h. And then we'll fix this h, and we just retrain the last layer. Usually the last layer, for both G or this specific F, for the target task, there are kind of simple function classes, like linear function or 1 or 2 layer neural network. Okay. By the way, if you have any question, you can interrupt me. I'm happy to answer during the talk. So this is a more formal formulation. Let's say we have T source task, each has N1 data points. So these are the notations for the source task. So you have X1T, Y1T, to X_N1T, Y_N1T, and T is from 1 to big T. So this is called a uniform path of sampling because each task you have the same number of data points. Later I'll talk about active sampling, where if you have different number of data for different number of data for different tasks, then you actually can further improve the performance there. So to learn the representation, which is this H function, what we do is to solve this kind of a bi-level optimization problem. So in the, say, outer loop, you try to minimize small h, and this h is shared across all T tasks. And here, let's focus on the linear prediction layer. So the last linear layer, we denote them as W1 to W big T. So you have T, K dimensional linear predictors. So K is the number, or K is the dimension of the representation. Okay. So you try to solve this objective function where you have some laws. Let's say for today, we'll focus on quadratic laws. And your prediction is this inner product between the linear predictor, WT for the small t task, and this representation, which maps input, says xit to a k-dimensional vector. And this laws measures how well you predict on this particular data. Okay. So here, for today's talk, we will not discuss optimization. We will assume you can really solve this problem using whatever algorithm, like gradient descent, and then we will analyze the solution of this objective function. All right. So this is how we use to learn the representation, and then for the new task, we just learn the predictor. Okay. Usually, you remember for the few-shot learning task I described in the beginning, we have very few data from the target task. Let's say we have NT+1 data, which is usually much smaller than N1. Okay, sorry, this N2 should be NT+1. And so sample from some distribution, and what we do is to learn this WT+1. So we fix the representation, learn from the previous the source task, and we just learn this last linear layer. So this is a convex optimization problem. It's a linear predictor learning problem, so it's easy to solve. So this is the frame setting we're gonna analyze. Okay. All right. So here, we consider a setting that we fix the previous layer, and there's some more recent work, I think by Jason and Chi, where they also analyze the meta-learning, where you can also change the H to some, training H during the predictor learning phase as well. All right, so let's first review what we know about from the classical statistical learning theory if you don't have representation learning. Okay, this is what we know. Suppose you only use the target task data. So you can get, so you will learn both the representation and the predictor together, and you solve this empirical risk minimization problem. What you can get is some theorem like this. Okay, so you have, remember for a target task, you only have NT+1 data. It's very small. And your loss can be bounded by this term, which is CH plus K divided by NT+1. Okay, so CH is some complexity measure of this representation class, just for this H. Okay, you can use number of variables, with dimension, number of complexity, those kind of learning theory complexity measures to capture how complex this function is. And then you have, because I have a k-dimensional linear predictor, you also have a k term here. Generally speaking, the CH is much bigger than k because usually we'll use like a very complicated neural network as representation, but you only use a linear predictor for your predictor specific layer. Okay, so this is what we know about, if supervised learning is well studied. Okay, so now what we need to show, we want to show and study is the when you can get a better bound using representation learning. So this is what we know for only using the target task, but here we want to understand if you use representation learning, why you can do better. So you can, in terms of theory, you hope to get a better bound than this one, okay? All right, so what we need, you can imagine, as I talked about before, if you don't have any assumption between the source task and target task, you cannot hope to achieve anything from the source task. Okay, so you do need some assumption. Okay, the first assumption, which is pretty natural, at least for this setting, is that there exists a good representation that is shared good representation that is good for both the source task and the target task. Okay, so formally, let's say there exists some h star, which belongs to this big H function class. So H star will map this input to a k-dimensional vector, and there exists a set of linear predictors, also k-dimensional, such that for both the source tasks and the target task, the composition of H star and W star will achieve, say, zero loss. So you can also generalize zero loss to some small loss. But basically, there exists a commonly, like a shared representation H star that is good for both the source task and the target task. Okay? So why this is a natural assumption? If you don't believe this is true, you should not use representation learning, at least for this framework in the first place, because this framework is really using you first learn the representation and then you fix representation to learn the target task. So if you know such representation exists, you should not use this framework or this procedure in the first place. Okay? So the next natural question is that if you have this assumption, then it is sufficient to show that you can improve the sample, like the bound for representation learning. Okay. So here we give here. Let me show you a very simple example that this assumption alone is not enough. Okay. So you need some further assumption in order to show that representation learning really helps. So let's consider this example. Say you have a 1,000 dimensional 0, 1 vectors. So they are the input. And I can tell you that the good representation is the first 100 dimensions. So the raw input is 1,000 dimension, but the good representation is just the first 100 dimension. So a good representation function is just a mapping from the 100, the raw input of 1,000 dimension to the first 100 dimension. Okay. And by good, I mean that all the tasks, both source and target tasks, only need the first 100 digits for the accurate prediction. And predicting, whether, like the task can be predicting the 10th digits 1 or predicting the sum of the first 100 digits. So let's consider this bad scenario. Okay, so if the source task, okay, although they all share the good representation of the first 100 digits, but the first source task only need to use first 50 digits. For example, predicting whether the 10th digit is 1 or not, but they only relies on using the first 50 digits. And there exists some target tasks that need to use all the first 100 digits. For example, predict the sum of the first 100 digits. Okay? You can imagine there can be some scenario like this where the source task, although they share the good representation for both the source and target task for the first 100 dimension, but in the real data you have, you only need to use the first 50 digits for the source task. So you don't learn anything about the 51st digits to the 100th digits. Right? So in this scenario, you can imagine you cannot learn a good representation for the target task because it needs the first 51st digits to the 100th digits, right? And this is really the worst case target task, which even though both source and target task share common good representation, it's not enough for representation learning to transfer from the source to the target task to improve the performance of the target task. All right, so what do we really need? We need kind of a diversity of the source task. Basically, what intuitively, representation learning is used for only if the source task, okay, can give the full information about this representation. Which is for the previous example, the source task should somehow cover the entire first 100 digits information in order to to learn the entire information about this good representation, and that's why it can transfer to any source target task in the downstream stage. Okay, so here we need to give a formal definition of diversity. Although this diversity definition should capture this intuition. So here's our definition. So here, remember, this is our first assumption. There exists a common good representation, H star. So what we need for this diversity is the following. So remember, we have T tasks, and it corresponds to, say, T k-dimensional vectors, W1 star to WT star. So this diversity, we mean it's this matrix, which is big W star, is a composition of W1 star to WT star, it's K by T matrix. It's a full rank matrix. Okay? So implicitly, we're assuming that T is at least big as K, so it can cover the span of the good representation. So why we call this is diversity? Because this W star, which is linear predictors for the source task, it really covers the entire kind of space of this representation. Okay. So for example, in the counter example I gave to you, the W star is not a full rank matrix. It is a low rank matrix and does not cover the entire span of the representation. Right? So here, let me give you some sample theorem we have based on these two assumptions. So with these two assumptions, you can actually show that you can improve the sample complexity bound compared with not using the representation learning. So this is the first example, which is called linear representation class. So the representation function is just a matrix which maps a d-dimensional vector to a k-dimensional vector, and d is the original input, and k is representation dimension, and k is much smaller than d. So the first assumption will become like this. There exists some b star of dimension k by d, and this set of vectors, w1 star to wt plus 1 star, the composition of b star x and w star, they achieve zero loss. So this is the theorem we can show. So under these two assumptions, we can get a bound like this. Okay, so we have two terms. The first term corresponds to learning the representation. The second term corresponds to learning the target predictor. Okay, so we have dk or n1 times the least singular value of this W star matrix square. Okay, so this least singular value under our assumption 2 is always positive because it is a full rank matrix. Okay. All right, so here let me give you some more concrete example. So let's say in the benign case, if you normalize the weight vectors for each task to be 1, and then in the benign case where you have, say, constant condition number for W star, then your least singular value of W star can be as large as square root of t by k. Okay, so if you plug in the square root of t by k back to this bound, you will have n1t in the denominator, and you have dk square in the numerator. Okay, and then you also have a second term. Okay, so the dk term represents learning this representation class, which is bk by d matrix. Okay, so if you compare in this benign case scenario and the directly learning the linear predictor without using representation learning, the bound will be d over nt plus 1. So first, if you compare the second term, k over nt plus 1 and d over nt plus 1, k is much smaller than d, so our second term is much smaller. For the first term, the denominator will be n1 times t. So remember, in the source task, we have a lot of data. And we have n1 data for t task. And it's much bigger than nt plus 1. So the first term, if you have a large number of data in the source task, much smaller than the second, than this term as well. So in this case, we show that under these two assumptions, you can actually decrease the error rate by a lot because you have, for learning representation, your denominator really the number of data in your source tasks. Okay. So this is for the simplest representation learning class. It's a linear class or subspace learning. We also have a more general results where we have a general function class, H star. And we have a similar result here. And instead of have DK here, we have some complex measure of this function class, which is CH. And the CH is some complex measure for the representation class, can be Gaussian width of this representation function class. So in the benign case, again, this least single value square can be T or K. So we have this kind of bond. And you can compare this bond with the without using representation learning bond. So again, we change the denominator, improve the denominator from NT plus 1 to N1T. So it is a big improvement when the source domain data is much, number of data is much bigger than the number of data in the target task. Okay? So we show that these two assumptions, they are kind of enough to show that you can improve the sample complexity using representation learning. Okay, so key takeaway message is that these two assumptions, the existence of a good representation for both the source and target task, and this diversity of the tasks are the key conditions that enable representation learning to improve the sample efficiency. Okay, so yeah, so this is pretty much about the first part of the talk. The second part of the talk, we want to further give a fine-grained characterization between the source and target task. So in the first part of the talk, the target task, basically you can be any worst-case target task. If you have these two assumptions, you can show improvement. But what if you have some more fine-grained connection between the source and target task, and then you can actually do better by doing more active sampling of the data. All right, so what we really need here is the notion of task relevance. Okay, so remember our goal for active learning is to select the most relevant source task for the target task. Suppose here you only have one target task, only one that you want to solve instead of many or the worst case target task. And you know this task, and you want to just select the most relevant source task to train your representation for the target task. So here we need to define, say, a relevance or like index between each source task and the target task in order to do the sampling. Okay, so here let me give you the example I gave you before. So again, we have 1,000 dimensional input vectors, they're one vectors. It's good representation is the first 100 dimension. So I give you this bad scenario where the source task only need to use first 50 digits, but the target task need to use the first 100 digits. In this case, if you don't have this diversity assumption, you cannot learn a good representation for the target task. So, but here you can consider this scenario. The source task, again, only use the first 50 digits, but if your target task also only uses the first digits, then you're fine, because you already have the information about the first 50 digits. Then you learn a good representation for the target task as well. So here notice that this is not kind of the worst case target task. This is more like a benign case of the target task. But if you're in this benign case, you can actually do better than the worst case. Okay, so here, let me give you the formal definition of our task relevance. So again, we have this assumption. We still need this assumption like you have a existence of good representation for both the source and target task. So here's our key definition of the task relevance. Okay, so first, we still need to assume the this WT plus 1 star, which is a linear predictor for the target task, lies in the span of the source task linear predictors, which is W1 star to WT star concatenation. It's a K by T matrix. Okay, so in the previous example, as long as it's equivalent to say that the first the target task also uses the first 50 digits. Okay, so you still need to at least you need to cover the linear predictor of the target task. Okay, but you don't need this W star to be big W star to be full rank. but you only need it lies in the span, WT plus star lies in the span of this big W star. Okay? So now, given this assumption, we know that there exists some vector such that you can represent WT1 star using the vectors of W star. And there are many to kind of interpolate WT plus star using the vectors in W star. Okay? And there exists many such coefficients. So here we define this like kind of the optimal interpolation in terms of the minimum norm of this interpolation coefficient. Okay, so there are many coefficients that can interpolate WT plus 1 star, but we choose those coefficients with a minimum L2 norm. Okay. Okay, so this will give you the uniqueness of those coefficients. Okay, so this nu, which is the coefficients, or this nu star with the optimal coefficients, is a t-dimensional vector. Okay, because you have t tasks, and each task we have a score to characterize the relevance between the source task and the target task. Okay, so in total you have t tasks. So this vector will be something like this. Okay, on my left, it's like 0.3, 0.4 to something like 0.5, something like that. So the S entry is the relevance between the source task I and the target task. Okay, so it's uniquely defined with this WT plus star and W star. Okay. So so here we minimize the norm to have a unique nu star, and so if you have nu star equals 1, it's equivalent to say that you have one source task that equals to the target task, and the others are orthogonal, meaning that WT1 stars or this vector is orthogonal to the other W stars in big W star. Okay, so this is one case where you have one nu star equals 1 for one entry and 0 for the other entries. All right, so here let me show you with this task relevance why we can improve the bound using active learning. So first, let's review what we know for passive learning. With this new definition. So what we can show here is basically the same proof as before, but we can show that you don't need, if this nu star exists, okay, so basically WT plus 1 star lies in the span of W star, then this is a kind of benign case. You don't really need the full rankness of W star. Then you can actually have a bound like this, okay? So it's dk times the the nu star norm square divided by n1 plus this second term. Okay, so here I want to do some active learning to further improve this bound, okay, from the theoretical point of view. And later I'll show you some experiments as well. All right, so first, let's imagine we know this nu star. This is definitely a very strong assumption. In practice, you don't know this nu star. But let's first design like a hypothetical algorithm with this known nu star. And later, we estimate this nu star iteratively. Okay. So instead of remember for passive learning, we have same number of data per source task. But here we sample the data according to this nu star t score. So for the small t source task, we sample proportional to this number. Okay, so let's say in total we have n1 t budget, just like the passive setting, but we don't sample them uniformly. We sample proportional to this nu t star score. And the other steps are the same. We still learn this representation using the bi-level optimization, and we fix this H and learn the last layer for the target task again. Okay, so the only thing we change is just instead of using a uniform sampling, we use like non-uniform sampling according to this task relevance. All right, so this is what we can show for known nu star. So we can have improve a bound something like this. It's kind of approximate sparsity. So let me explain here. So you have dk s star times nu star square new star norm score. And second term is the same for both the active and or passive learning. Okay, so this S star is kind of truncated, approximate sparsity. So if it's bigger than some threshold, then we truncate it to be 1. If it's smaller, then it's 0. And it's defined in this way. All right, so remember, if you have passive sampling, you have dk times norm, this new star norm square divided by n1. Okay, so first you can show that this bound is never worse than the passive sampling, so we're not losing anything if you can do this active learning. And here, for certain scenario, we can do much better. So here's consider this example. So you have one source task equals to the target task, but the others are orthogonal, and you know this task relevance. So here, you can show that S star equals 1, new star equals 1 for one entry. And then if you compare these two bound, okay, so you have S star equals 1 in the active learning bound, and in the passive learning bound, you don't have this S star, and S star equals 1. So you can have 1/T improvement over the passive sampling. Okay, so this is one scenario you have a clear improvement. So what is the intuition for this example? So suppose you have in total T source tasks, and there's one source task that is exactly equal to the target task. And you can do active sampling from this source task. So what you should do? In the passive sampling, you just uniform sample from all the source tasks. Then you waste most of your data because you are sampling from those orthogonal tasks to the target task. So what you should do is just use all your budget to sample from this source task that is equals to the target task. So use all your budget, just sample from this one particular task. Then definitely you will have a 1/T improvement in terms of the sample complexity. Okay, so that's the intuition. Again, but our bound is more kind of adaptive. It adapts to many other scenarios as well. But this is one takeaway example that if you have one source task that equals to the target task, then you should just sample just from this source task. And you should not waste your sample from the other orthogonal tasks. Okay? So if you don't know this new star, we can actually just iteratively estimate it. So basically, we have two ideas, kind of similar to online learning or bandits. We can estimate new star iteratively and use a doubling schedule. So we first initialize some estimation, new hat T to be 1 for all the tasks. And at each epoch, we sample according to our formula, which is proportional to this estimated new T hat square. And for the jth epoch, we sample, say, proportion to the, say, 2 to the j samples. Okay, and then we learn representation, we learn the linear predictor for target task, and we solve this linear program. This convex program to estimate this new hat, okay, and then repeat it. So this is a doubling schedule, and we iteratively estimate new star. So if we have unknown new star, we have some lower order term which accounts for estimating this new star. But the other terms are the same. So you can still get some improvement. You have generally large amount of data. All right, so here let me show you some interesting experiments. We compare active learning and passive learning. Okay, so this is a data set. It's called MNIST corruption. So we formulated it as a multitask representation learning setting. Here there are 16 types of corruptions. So these are the 15 types, and there's like original image, which is the 16th type of corruption, which is basically no corruption. Okay, so here we construct a multitask learning setting. So we have 10 digits and 16 types of corruption. So in total, we have 160 binary tasks. And each target task has 150 source tasks, which correspond to 10 digits, and 15 other types of corruptions. So we have in total 160 target tasks for testing. And for each task, we construct like 150 source tasks to learn representation. So here, we consider two kind of representation function. One is the linear low-rank representation, or basically it's subspace learning. And the other one is a two-layer neural network for this image data. Okay, so here's our experimental results. On the left is the heat map of the improvement. If it's positive, this shows the improvement of using active learning or active sampling or the passive uniform sampling. So you can see here the majority of the, most of the numbers are positive, and there's some summary statistics. So for average, okay, so for each column, it corresponds to one digit, and each row corresponds to one kind of corruption. Okay, so the average improvement is 1.1%, and this is still significant because the baseline error is around 8%. Okay, and the positive improvement is 136, or in total 160 tasks. And on the right, you can see this histogram where this orange curve corresponds to our active learning. It's called add up. So it's shift to the left, which corresponds to with a smaller arrow. And the blue curve is the original non-adaptive sampling. Okay. So this is for linear representation. You get this kind of improvement. Oh, by the way, so this is you improve. This is using the same number of budget for source task. So if you have, in another setting where you have some target arrow, then it's equivalent to say that for a certain target arrow, you can use fewer data to achieve this error rate. So using this active learning. So these are results for convolutional neural network. The results are similar. The baseline is stronger because we use a stronger function class for representation. The baseline error is 6%. And then here we get 0.68% improvement. All right, so another, and most of the tasks we had positive improvement. All right, so in the last part, I want to talk about one interesting observation from our experiments is that you can actually, learn this reference. Actually, you have some expandability using our definition of task relevance. Okay, so this is one example from our experiments. There are many similar examples. So this is for that our target task is to classify whether an image is digit 2 or not, and the corruption is called glass blur. And this is the heat map we learned for the task relevance, the new star we learned. Okay, so you can see here, we have 150 source tasks, and this is task relevance for those source tasks, for task relevance scores. So you can see here, because this target task is about classifying whether the image is 2 or not, you can see here we find that the task relevance score for other source tasks is also about classifying this image 2 is 2 or not, has a much bigger volume, which corresponds to the third column of this left histogram. Okay, so you can see here there are many bright cells, and those correspond to a very large task relevance score for those source tasks. And they are also about classifying whether a digit is 2 or not. So this can be used as a way to provide an expandability for representation learning. So this is for linear subspace learning. For ConvNet, the situation is more complicated. The many cells in digit 2 is still very bright, but there are also many other cells that are also bright also. So for convolutional neural network is nonlinear, so there's something unknown going there as well. And this is left as an open problem. All right, so this gives you some expandability about the relevance between tasks, and this is purely learned by the data. We did not impose any prior knowledge about this. These tasks. All right, so in summary, for the second part, I believe active learning is very useful in representation learning and is underexplored. Okay, and here we give a formal definition of task relevance, and we show that it can be stronger than passive learning in both theory and practice, and also the score gives you some interpretability as well. For future work, generally, I believe there's a huge potential of active learning for representation learning or the general data selection. We can do some more principal methods to learn representation learning for pre-training. Here, we learn everything from scratch, but nowadays, if you have a GPT-3, you do not purely learn from scratch. You will have some pre-trained model, and then you fine-tune on top of that, and you can still do active learning for that. There can be other definitions of task relevance, not using our minimum norm, but there can be other relevance to capture the connection between different tasks. And then lastly, you can also study other representation learning frameworks like contrastive learning. Can you do active contrastive learning there? That concludes my talk. I'm happy to take some questions.
Okay, thanks, Simon, for the great talk. Any questions?
Hi, thank you so much for the very refreshing talk. I have two quick questions. The first one is, how sensitive are these results to the realizability assumption?
That's a good question. So you can show some like agnostic bound for supervised learning. For the active learning part, we didn't analyze. I believe you can get some similar bound. And experimentally, it's definitely not realizable, and it still works.
Exactly.
Yeah.
Great. And the second question pertains this assumption of task relevance. So if the predictors that I have are linear, then it's very clear that I should enforce my target predictor to be spanned by the previous ones. Yeah. So how should I understand this assumption in the nonlinear case?
It's largely open, I would say. There's at least one paper studying that using some kind of eluded dimension to capture the connection between the source and target task, but for it's hard to generalize that to the active learning setting. So yeah, it's still open. I think it's still kind of open for nonlinear predictors.
Awesome. Thank you so much.
Any other?
Thank you. Hey, how did you define the V star for the convenant experiment? Was this in the parameter space or like?
Oh, it's always in the, so new star is always defined as the last linear, using the last linear layer. So you can always define it, define this task relevance or this new star on whatever representation function you're using, as long as your predictor is a linear layer.
I see. So there's no nonlinear part before.
Yeah, there's a nonlinear before for representation, and there's a linear for predicting.
I see. Okay, thanks.
In your assumption, you had that W star lies in the span of the Ws. Is it possible to also get a bound where there's not a perfect W star that lies in the span, but there's something else that lies in the span with a very small error?
I think the analysis should work there. Like you have some agnostic bound that depends on the complementary space of the WT plus 1 star.
Okay, thank you.
Could you comment a little bit more on how the S parameter depends on the doubling procedure or how you sample from new star?
Okay. So the S star parameter is kind of approximate sparsity. Like if it's very sparse, then which means that there are only a few source tasks that are actually relevant to the target task. And so it's also, it's defined through new stars, so you can sample according to new star based on that. Is that the question you're asking?
Yeah, I was basically interested in sort of how does the norm that you minimize? So essentially you take the minimum L2 norm new star.
Oh yeah, that's a good question. So here we use L2 norm because we can kind of recover the result in the supervised learning. But we also have an ongoing work. We actually can, you can generalize L2 norm to some L1 norm and actually can get better bounds. I think we'll release it in a few months. Yeah.
Right, because more pointy norms may make more sense because
Yeah, exactly. Yeah, right. Especially for sparsity, it makes more sense to use L1 instead of L2 there.
Right. Thank you.
Have you looked at how sensitive new star is to changes in the initialization or maybe the architecture?
I think we done some ablation study there. It's not very sensitive, at least for our, because we only tested kind of simple representation function, so not very sensitive. But yeah, it's interesting to test on larger models in terms of initialization.
Hello. So in your setting, you trained only for the target task. You trained only this linear of dimension k vector, right?
Yeah.
So it means that we can easily have something like under-parameterized situation where, for example, the number of, even in target task, the number of samples is bigger than k, because this k is usually it's like 1,000 or less.
Yeah.
So is it, do you expect something here, so some quality of different behavior if we have this target task is under-parameterized or over-parameterized? Because in our like standard cases, usually it's important in which regime we are over-parameterized.
So yeah, so most of all my work so for this talk is kind of under-parameterized setting where the n is bigger than the complexity of the predictor. There are some work that extend to the over-parameterized setting. But the bound will be more complicated and depend on certain complexity of the predictors and the function class.
Okay, thank you.